Welcome to Crystallography and Crystal Structures. This is MSE 3134 for 3 credits, and I am Dr. Maureen M. Julian. The crystallography text will be Foundations of Crystallography, 2nd edition, and we will also use the student edition of the International Tables. And later in the semester we will use an eye clicker. We also have a crystallography website, and here it is. And on the website you'll find an electronic form of the starter programs for each of the chapters. You'll find the homework problems chapter by chapter. The material will also be found on Scholar for this course. Another important source of data is the Cambridge database. In this picture you can see 3 molecules out of the 750,000 molecules in this database: caffeine, aspirin, and glycine. We don't have minerals or the very large biologic molecules, but we do have other databases. And Virginia Tech has access to the complete database everywhere on campus. One of the most important pieces of information for collecting data is the CIF file, the Crystallographic Information File. And this is an electronic archiving file for crystallographic data. You will be collecting CIF file. This is what your CIF file will look like when you collect it from the Cambridge database. This formatting begins it. And now we have the CIF file for caffeine. The name for caffeine is, the reference name is CAFINE, and the actual chemical name is given down here. Usually there are a combination of letters that you can't pronounce, and you'll notice them when you collect your own data. And here is the information about the journal and where it was published. Here's information about the refinement and the symmetry of the crystal. Here's some of the unit cells information, and here is the information for the location of the atoms. You will use this in your Festival of Crystal project. Everyone will choose a crystal from the list which RTAs will post, and you will perform calculations on your own crystal throughout the semester, and then these exercises will be collected and summarized for your final Festival of Crystals and for your final. Selecting your crystal, look at the list of crystals which will be posted by the TAs. For this class we have a volume of about 700 cubic angstroms to keep the level of difficulty for each of the students the same. If you're interested in a metal, you can choose an organometallic. If you're interested in a ceramic, choose a crystal with a cation and an anion. If you're interested in polymers, choose a polymer. There are many biomaterials, and you may, however, select any crystal from the list that is posts. Here's some examples from another class, not from your class, and here is the reference name, and you can see they're really funny combinations of letters. Here is your crystals, and this is the formula. So this would be C24H18, silver, N4, oxygen, all +1, and then O4Re -1. So this is a ceramic because you have an anion and a cation, and it's an organometallic because it has metal ion atoms present. This is just a plain organometallic. You can see here's the manganese in here, and if you want a polymer, here you see the little N which is which will be a subscript when you write that out formally. The learning objectives for this course is 1. To use crystallographic databases, to understand the CIF file, to describe mathematically basic vectors and the transformation between basis vectors, calculating interatomic bonds and bond angles using the metric matrix, describing rotation and mirror symmetry operations and their related matrices, defining the point groups and understanding their relationship to the point group tree, and likewise describing the relationships between space groups and point groups, and again the space groups will have their own tree too, and relating the reciprocal lattice to the direct lattice, relating Bragg's law to the diffraction spectra, calculating the scattering factor curves, and interpreting the published crystallographic data in terms of your own crystal. The first group has to do mainly with the symmetries, and then the second group is more relates to the actual collection of the data. This course is divided essentially the book is divided into 3 parts. First is the foundations of crystallography, which is the theoretical background in chapters 1 through 4. The experimental crystallography is picked up in chapters, actually that should be 5 through 7, and part 3 starts out with a bridging chapter of 8 and then continues on from 8 through 9 through 15 with examples, extensive crystallographic examples from each of the 7 crystal systems. And here is the way the course is divided. The format is that we'll have 3 tests and a final. Test 1 and Test 2 are closed book. Test 3 and the final will relate to your project, and the project will be the Festival of Crystals, which will be an oral presentation. In order to keep everybody on track, we'll have a weekly quiz on every Wednesday. The first one is this coming Wednesday. The chapter objectives for lattices are: first, to recognize the crystal as a repeating pattern; second, to associate a unique lattice with every repeating pattern; describe the lattice with basis vectors; distinguish the handedness of the basis vectors; and mathematically describe the lattice. Then we will leave the orthonormal world and realize that basis vectors need not be orthogonal or unit lengths. We will describe the lattice with more than one set of basis vectors, and we'll associate a unit cell with these basis vectors and study the transformation between sets of basis vectors. Because if you index a cell with one set of basic vectors and I with another, how do we know whether we have the same crystal or not? So we have to be able to transform. And the first chapter will also expand the concept of lattices from 2 to 3 dimensions. We will construct a transformation matrix between the crystallographic and the Cartesian coordinates so that we can use the graphics, computer graphics. And we will construct, using computer programs, a unit cell for any crystal, including your own special crystal, given the lattice parameters from the literature. Finally, we will observe the variations in lattice parameters with temperature and pressure in general. If the temperature goes up, the lattice parameters will expand, and as you squeeze the crystal, the lattice values will decrease.